This is the introduction to your pipe loss pre-lab for the pipe loss experiment. Before I get started, I'd like to just let you know what we'll be going over today. The first thing is just an overview of what we're dealing with the piping system, what kind of flow we're looking at, and some common applications that this could be used for. Also, I'll be going over all the calculations that are necessary for the report that you'll be writing and for the analysis of the system. So the first thing is the common applications a piping system is used for. And this is actually a very good experiment because it lets you see in real life what you're working with and what you might see later in industry. The piping systems like this are used for heating and cooling for buildings. They're used to pump water from aquifers to the city water supply. They're used throughout automotive engines. They're used very extensively. So understanding all the different losses that contribute to the output of the system is really important so that you know how to better design a system like this in the future. What we'll be working with is internal flow and circular pipes, and we'll be working with water that's provided by the lab. We'd like to focus here on fully developed flow because we really don't have a lot of theoretical accuracy with the transitional flow, and you'll need to make sure that the piping system is arranged in such a way that you can actually attain fully developed flow and that you're not in a region where the entry effects are creating a disturbance in your flow and not allowing it to become fully developed. We'll be looking at the laminar and tubular flow, which I will address later when we look at the parameters we'll be calculating. And another thing that we'll be looking at is the Reynolds number, which I'm sure you've been introduced to before, but just as a reminder, the Reynolds number is a ratio of the inertial forces to the viscous forces. So for a higher Reynolds number, your inertial forces overcome your viscous forces, which leads to turbulent flow, and in a lower Reynolds number, your viscous forces are greater than your are larger compared to your inertial forces, and that's where you get laminar flow. So for your report requirements, you'll be writing a letter explaining the experiment and going through everything which is listed on the website, and you'll also be going through and calculating a few different parameters. I'd like to get started now with the different parameters that you'll be calculating. So for the entry length, to ensure that that's not affecting the development of your flow, you need to make sure that the length before it gets to the point you're measuring is greater than certain values. So for laminar flow, you have a hydraulic entry length which can be approximated as 0.05 times your Reynolds number times the diameter of your pipe. And for turbulent flow, you can approximate this as 10 times the diameter of your pipe. The next thing that we'll be looking at is the friction factor within the pipes and also the Reynolds number of the flow through the pipes. And the friction factor, move over here, can be calculated from the experimental values based on this equation, which is given in your book. So it's the change in pressure over the quantity 1/2 times the density of the fluid times the velocity of the flow times the quantity of the length of pipe over the diameter of the pipe. And this expression, I'll show you in the uncertainty calculations, will actually be converted into terms of only measured values, so that when you do your uncertainty, it's easier to understand where these uncertainty contributions are coming from. So I'd also like to show you the Reynolds number here, which is the density of your fluid times the velocity of your flow times the diameter of the pipe over mu. And these two are going to be based on measured values, as I mentioned. So these two parameters, you will have to convert them into terms of measured parameters, and then when you do your uncertainty, we will need to see exactly what uncertainty we're getting, which is from these contributions. And these will both be used in some of your graphs for your report. What you're going to be comparing also is you want to look at the theoretical friction factor in addition to what you've measured. And the theoretical friction factor can be found from the Colbert equation. .7 plus 0.51. And this equation is going to require a simultaneous solution process to solve for the friction factors, which is located on both sides of the equation. Now you can use Excel or you can use trial and error to find this. The way that you want to start is by assuming your relative roughness for your pipe based on the industry standards for that pipe, and then calculate the theoretical friction factor. And from there, see how it compares to what you got experimentally. And by varying this relative roughness, you can actually see what roughness is more accurate for what we're seeing in the experiment. So that allows you to actually see if the industry standard is really accurate for what we're looking at. And then you can, of course, discuss why it is or why it's not. For laminar flow, the theoretical friction factor is calculated based only on your Reynolds number. So this is for turbulent flow. And this is for laminar flow. Okay, so these will be used for your major losses, which will be the length of pipe that you'll be looking at. So in the experiment, as you'll see in the experiment video, there are two major losses that you're looking at, and then there's a minor loss due to the elbow. So the major losses are just the frictional effects that the piping system sees due to the length of pipe that the fluid is flowing through. And that's what you will use these for. For the minor losses, we'll be looking at a 90-degree elbow, and to calculate that loss coefficient, you use this expression. And this expression is going to tell you the loss coefficient at different flow rates, since this is your velocity of your flow. And the head loss can be calculated simply by the difference in the heights of water measured in your experiment. So your head loss is equal to H1 minus H2. And again, there's an example of this in the information on this lab on the website, which will show you how you'd be measuring the height of the water and where the difference comes from. These are the values that you'll be using when you're plotting your graphs for the report. And when you plot these, you also would need to include the uncertainty bar so that the person you're writing this report for, which is some engineering firm in this case, will have some idea of how certain you are that these results are actually correct and accurate. So the way that you need to do that is look at the values that include parameters that were measured. For instance, your friction factor, which I wrote up here. This value will need to be converted, as I mentioned, in terms of only the measured parameters. So we know that delta P is equal to H1 minus H2 times rho G. So in this case, we measured this, we measured this. Gravity has some uncertainty associated with it, and I believe the rows end up canceling out. So then you're looking at the velocity of the flow, which is equal to the flow rate over the area. The flow rate was measured directly in the lab. The area was actually measured also, but it's in terms of pi and the diameter. These are just the terms, not the expression. And we measured directly the diameter, we measured directly the flow rate, measured the two heights, and then what happens with this equation is the whole equation, which I will write over here. The equation becomes in terms of H1, H2, Q, D, L, G, and pi, where H1 is the first height measurement, H2 is the second height measurement, Q is your flow rate, D is the diameter of your pipe, and L is the length between the 2 points at which you measured. So this is also something you'll need to measure in the lab and keep track of the uncertainty in that measurement. G is the gravity, and pi is pi. Now, just because these two aren't measured doesn't mean there's not some uncertainty associated with them. So you need to be careful of that. And once you have your friction factor in terms of all of these quantities, you'll be looking at the root sum square expression to express the uncertainty of the friction factor. So I'm sure you guys have seen this before, and if you need a lot of detailed information on it, there's more information on the website. There's actually a whole document that goes over the uncertainty calculations. But I'm just going to show you a general formula here to give you an idea of what this root sum square method is. So to get the uncertainty of the friction factor, we will use this expression, where we'll be looking at the partial derivatives with respect to each of the measured and constant parameters. So we'll do, now you could do it two ways. You could either do a delta H or you could do each one individually. It should come out the same because your delta H is going to take into account the uncertainty of both values. So for this, I'll just show you H times the uncertainty of H. This is squared, plus partial derivative of the friction factor with respect to Q. Ooh, that didn't come out very good. Times the uncertainty of Q. And your last one would be with respect to pi. Times the uncertainty of pi. And this expression is going to give you the total uncertainty for the friction factor. Now, the best way to do this is to put all of your data into a spreadsheet and to set it up so that you can type this expression in one time and that these different values will change. So you'll just have to calculate your partial derivatives, and you'll have to have a column that shows the uncertainty of each value at each different flow rate. And once you have all that in a spreadsheet, it's really easy to put this equation in once and then drag it down, and you have your uncertainty at each point. So this will need to be done for the friction factor, also for your Reynolds number, and for anything else that you're measuring and plotting. So in the lab report, you need to plot your head loss versus flow rate and your friction factor versus Reynolds number. So for your head loss versus flow rate, you'll also need to include the uncertainties, but they shouldn't be this complicated because those values were directly measured. What you'll be doing with this information is that when you plot your points, well, first you'll need to show the sample calculation so that we know that you understand how to calculate the uncertainty. But also, when you plot your data points, let's say you have something like this, and this is Reynolds, and that's friction. So now this is probably not exactly how yours will look, but just to give you an idea of what we'll be using the uncertainty for, we'll need you to put uncertainty bars on these data points to show the reader exactly how certain you are that your data point is in the correct place. So in this case, if your bars are this big, you have a very large uncertainty in this data point. If that's the case, you'd need to explain why is the uncertainty so high and what could you do to bring down that uncertainty so that you have a better idea of where that data point should be. You may have uncertainty bars that change for the different points, and if there's one that's not consistent with the others, you also should explain why that is. Also, this would just be expressing the uncertainty for the friction factor. If you also want to express the uncertainty for the Reynolds number, you'll end up with bars on these sides. Etc. So that will be the trend of how your data will look, and that would be the best explanation of how confident you are that your data is correct. Okay, I think that concludes the pre-lab lecture for the pipe loss experiment. If you have any questions on the guidelines, on the report requirements, please ask a TA or your professor to make sure that you understand it before you turn it in. And if it's ambiguous, of course we want to clarify and make sure that everyone understands. So that should be it. Thank you.
Okay, I want to describe the apparatus that we're going to use in this lab. So I'm going to begin by tracing the flow of water through the pipes. So the water begins down here in this storage tank right here. This is the beginning. It's going to be hard to see, but when you get to lab, I want you to just follow through on this. There's a pipe that comes out of here, out of the end, a tube, actually it's a rubber tube, and it comes out and it goes into a motor, which is down here on the floor. You might not be able to see it. It goes into this motor pump assembly, which boosts the pressure. And it comes up, and this apparatus down here, the water comes up, and normally it will come out of this pipe right here and go into this, what we could call a manifold over here. Now this set of pipes down here is set up so that if we shut the flow off, or we shut it off too much, there's a bypass valve so that the pump doesn't get overloaded, and it will go back through this tube over here and back into the pipe up here, or I'm sorry, back into the tank over here. But normally the flow is going to come out of here and it's going to go into these pipes over here. And when it gets here, when it enters here, it can either make a left or right turn or actually go both ways. Now, in order for it to go through the large pipe, we'll set up a valve over there, I'll show you in a minute, but if it goes through the large pipe, it'll make a left turn and come up here to the top, and it'll go through this large pipe over here. Then we'll come out at the other end here, and it will go up, and depending on how you set the valves up over here, it'll go into one of these three pipes where it'll pass through a flow meter, and I'll go over this in more detail in a minute. And then it will come out and it'll go through this pipe. There's a sight gauge right here so you can see if you have flow. And then it comes through, we have an analog gauge here for the flow meter. It goes through this pipe, comes around, and then goes up here. It hits the control valve, comes back over here, and then it goes back into the tank over here. So that's the path of the water for the large pipe. For the small pipe, it will take a right turn here and then just go through the small pipe like that, and then we'll follow the same path. So when you get to lab, the first thing you ought to do is just trace that flow path so you'll know where the water is going. All right, in order for it to get the water to go where you want it to go, we have two valves. There are more than two valves on the system, but there are two important valves. There's the valve here on this small pipe right here, and there's a ball valve here on the large pipe. In order to get the flow to go through the large pipe, we open the large valve, the handle will be in line with the pipe, and we close the small pipe, so it'll be at a right angle to the flow, like that. Okay, so now the flow will go through the large pipe. In order to choose the flow meter, we open the valve to the flow meter we want. So we have three flow meters here. We have our large flow, medium flow, and low flow. you want to choose the flow meter that's most appropriate for the flow that you have. So you want to be operating at the upper end of the range for the flow meter. Okay, so if we want it to go through the large flow meter, then we just close the valves for the other two, and now we'll only go through that flow meter right there. If we want it to go through the medium one, we open the medium valve and close the top one. And then to go through the small one, we just open the small valve, the small flow valve, and close the other two. Okay, so I'm going to open it so it goes through the medium flow right now. All right, if we want the flow to go through the large pipe, you just trace the flow back over here. We want to close, if we want it to go through the small pipe, we open the small pipe valve and close the large pipe valve. So now the flow will go through the small pipe, and it will follow the same path. Okay, there are other valves on here, but they're only used for maintenance, so you don't have to worry about those except for one of them. In order to control the flow, we have a valve up here that's labeled the control valve. And so right now it's wide open, so we have the maximum flow. If we want to reduce the flow, we just turn it like this, and then you adjust it to whatever flow rate you want until it's ultimately all the way closed like that. Normally we don't want to operate it with the valve completely closed because that's going to put a big load on the pump and create a problem. And there's really no reason why we need a zero flow rate, because at a zero flow rate our friction factors and so forth have no meaning. Okay, so we'll open that up. In order to measure the pressure losses, we have several instruments. The way what you're going to use for your data is we have a transducer. So we have a pressure tap right here on this large pipe, and we have another one over here. So the flow is going in this direction, so there's going to be some pressure loss in the pipe. So we have in parallel with the pipe, we have a pressure transducer. This is a differential pressure transducer, and it sends out a voltage to LabVIEW, and we can use that to measure the pressure drop. We also have hooked up with this an analog gauge. So this gauge right here, you can follow the pipes here, or the tubes, but we have this analog gauge right here, so you can also look at this gauge and see what the pressure difference is. This gauge and the pressure transducer might be a little different because water can actually go up in the tubes here, and that's going to change the reading a little bit. So this should be a little more, the transducer should be more accurate, but this will give you an idea of what's going on. We also have a transducer for the small pipe, which is located down here, and you should find that when you come to lab, and we have an analog gauge associated with that. And then finally, we have an elbow right here. So the elbow is part of the large pipe assembly. And so the flow comes in here and it goes across that elbow, and we have a transducer that's located one upstream and one downstream of the elbow, and it goes to a transducer, and we also have an analog gauge associated with that. So you can see what's going on at the same time we're measuring it in LabVIEW. We also have a few other pressure gauges located around, so you want to look at those. Okay, so right here is a gauge pressure gauge, which measures the gauge pressure coming out of the pump. So this is the pressure directly out of the pump. With the valve all the way open, it should be between somewhere 25 and 40 psi. If we close the valve down, we can get it to almost 300 psi. And then as we go downstream, I have a few other pressure gauges. I have one right here, which is just prior to the control valve, and you'll see that this pressure is probably going to be a lot less than what's coming out of the pump because we have a lot of losses in the pipe system. After it crosses the control valve, there's another gauge up here, and you'll notice this one actually is an absolute, well, it shows gauge pressure, but it'll show a negative pressure. And I put that there because it turns out that the pump is actually creating a suction downstream of this sometimes, and the pressure in here is going to be very low. There's a pressure gauge on the tank, and if you look at that, you would probably expect it to be pressurized, but actually it's probably going to have a slight negative pressure in it. So this tank is, contrary to what you might think, it'll have a negative pressure in it. Okay, we have an analog flow meter right here, which you can use just to visually see what's going on. Now, in order to collect your data, you're going to come over here to the computer, and LabVIEW may or may not be on. So you're going to go to the user is going to be NSC312, and there's no password. You bring it up, I've already done that. And then right here in the middle of the desktop is the icon for this particular LabVIEW program. You double click on it, and it'll bring it up. While that's coming up, there's some other things you'll need to know for the lab. One is, it asks for the pressure in the room. We have a mercury manometer in the middle room where the TAs are. You can, and the TA can show you how to use that. And then we have thermometers scattered around the room. There's one right here, and I've labeled it thermometer, hanging right on the equipment itself. Okay, so now LabVIEW has come up, and it's got gauges for the flow meters, and then the differential pressure gauges, and then also the pump output. So in order to run this, we hit the run button over here on LabVIEW. I know you probably can't see this on the camera, but we hit it, and it will start to run, and you should get some little numbers up here. They all should be close to 0. We're ready to run it. I'm going to go ahead and start this, but you probably won't be able to hear me, so I'll just run it for a couple of seconds. This is the on switch right here. So I turn the pump on, and we make sure we have flow. So you just want to look down here and make sure there's some pressure coming out, and we should have flow. These gauges will start to move around, and you can look at the sight gauge, and you'll see there's a little arrow that's pointing in this direction. That tells you we have flow. And then you'll also see that whatever flow meter you have open should start to register. Right now we have the middle one open, and it's reading 35.3 liters per minute. So we want to set the flow. So it tells you in the write-up what flow rates to set. So, for example, this is wide open. That would be one of my settings. If I want to set a lower flow rate, then I just adjust the control valve until I get the flow rate that I want on the screen here. Okay, so I just adjusted it. And I adjusted it so that it came down to 33 liters per minute. Okay, I'm going to turn the pump off now so you can hear me better. All right, so once you sit here and you get it going, it's what I call idling now. The program, I call it idling. It's idling, and you can set the flow rate that you want. Then when you're ready to collect data, you have a window over here, and it says push here to collect data. And there are 3 settings. There's a sampling rate, samples per second, and the runtime. So you pick an appropriate sampling rate and frequency and runtime. I've got it set right now for 3 seconds. So it says push here to collect data. So I'll hit the button, and it'll collect data for 3 seconds. And then when it's done, a spreadsheet will pop up. And you come up here to the top, right in the upper right-hand corner, it says Save. You click on Save, and then you type it. Make sure you're in the pipe loss data folder, and you can create your own folder at this point. Type in the file name, and then hit OK, and it will save it. And if you just type in a file name with no extension, it'll save it as a text file, but you can open it with Excel, or you can save it as a file name .xls or something like that. Okay, and then you have your data. So then you do it for your different runs, whatever settings you have. So you'll do it for the big pipe, the small pipe, the elbow, and I think that might be it, but whatever it says in the lab write-up. I also want you to, I have an extra control valve right here, and I want you to look inside of it. This one's a little bit smaller than that one, but it's the same geometry. And so, let me take these out. So you look inside, and you can see it's a ball valve, but it has a kind of a special geometry to it. So sit here and open and close it so you can see how it operates. And I'll have it sitting right up here in the area. And then also in your lab report, there's a set of fittings over here that you're going to need to identify. So they're in this box right here, and they'll be in the vicinity of the lab. And so I want you to look at each one of them, and I just want you to look inside of it and operate them, and you can see what different types there are. And they're numbered. This one's numbered 3. And so for your lab report, there are 10 valves or different valves, and you're going to have to say what type they are. So for example, this one is a ball valve, number 3. And then we have number 1 here, it's a check valve. You can see how that operates. It only allows flow in one direction. And then we have a few others. And just look, like these two look identical, but they are not. And if you look inside the valve, you'll see how they operate. And each one of them will have a different loss coefficient. And they have their own applications. And so part of your lab report is to identify these and identify applications and the loss coefficients. There are other valves here. For example, this one says do not touch, so do not touch that. And I think that pretty much takes care of operating the apparatus. Thank you.